Hello. During World War I, there was a fishing village in Italy that kept track of how many fish were caught each year by the Italian fishermen. And as the war took away more and more fishermen, you would think that would have been good for the fish, but instead it actually hurt the fish. And so the question is, how can that be? And can mathematics explain that phenomenon? And that's the topic of our section in these next couple of videos about systems of difference equations. But before we analyze that more complicated situation, let's look at a simpler one. And that's going to involve a rental car company. So imagine we're starting a company and we're going to have two offices, one in Kansas City and one in Emporia. And there's going to be some people that rent a car in Emporia and bring it back to Emporia. And let's say that's 75% of those cars. And the other 25% are going to take them to Kansas City. On the other hand, if one rents a car in Kansas City, let's say 85% will bring them back. And let's say the other 15% take them to Emporia. And so the question is, can we model this behavior using difference equations? For instance, let's say we started with 100 cars in Emporia. What would the day-to-day change be? Or if we had an equal number in each city, would that change the long-term behavior? Or if we want to know what would be the optimal way to start, if we're starting a new business, how many cars should we put in each city to maintain some sort of equilibrium? Now, keep in mind, this is another example of a messy problem where people's behaviors don't necessarily match these numbers perfectly. These are more of a probabilistic sort of number. But for now, we're going to assume that the percentages are exact for each day. And that each rental is for one day. So that would be another complicating factor where some people rent a car for a couple of days or a week, or they take it to another location. But again, we're keeping it simple just to illustrate the point of systems of difference equations. So let's start with this question. If Emporia starts with 100 cars and Kansas City 0, how many will be in each city each day? Okay, and then we'll analyze some other questions when we're done with that. So let's see if we can use difference equations to model this. So to get rolling, we need to let E sub n equal the number of cars in Emporia after n days. And we'll let K sub n equal basically the same thing, but in Kansas City. Now, based on our diagram up here, we can make some difference equations. For instance, we can say that E sub n plus 1 is equal to, so in other words, the future number of cars in Emporia is going to be 75% of the number of cars that were in Emporia the previous day, so 0.75 en, plus 15% of the cars that were in Kansas City the day before. So E sub n plus 1 is equal to 0.75 E sub n plus 0.15 K sub n. Likewise, for Kansas City, we can say that K sub n plus 1 is equal to 0.85 K sub n plus 0.25 E sub n. Just like before, we need initial values. We're for now assuming that 0 cars are in Kansas City and 100 cars are in Emporia. And the number of cars is constant. So this company has a fleet of 100 cars. So let's try this out on the spreadsheet and then we'll go from there. So here's our spreadsheet, and we're just going to track it for 10 days for now. And we'll go ahead and start with 100 cars in Emporia and 0 in Kansas City. And so a spreadsheet, as we've seen before, works great for recursive relationships. So I'm going to write 0.75 times the previous number of cars in Emporia, so that's so, plus 0.15 times the number of cars in Kansas City the previous day. And so as expected, there's 75 cars in Emporia. And then we can do the same thing for the next one, 0.85 times the previous number of cars in Kansas City, plus 0.25 times the previous number of cars in Emporia. And the good news is this still adds up to 100, so that looks promising. We can drag this down. Now, of course, the nature of it is we're going to get decimal numbers. That doesn't make sense for cars, so we'll just go ahead and round that to the nearest integer. And notice over time, it starts to level off until it appears we're reaching an equilibrium, because notice for 2 days in a row, we have 38 cars in Emporia and 62 in Kansas City. Now, what would change if we had started with 50 in each city, for example? Notice the final outcome stays the same, although we do get there quicker. If we had started with 100 in Kansas City, it takes maybe a little less time than the first example, but we still end up with somewhere around 37 or 38 and 62 or 63 in Kansas City. And if I had started with the equilibrium value, then notice nothing ever changes. So if we wanted to have less movement and meet the demand that people presumably would want, I should start with 38 cars in Emporia, 62 in Kansas City, and then that would stay constant throughout. Now, as we said, that's not going to work perfectly in the real world, but if we're looking for what would be a ballpark number to get us in the vicinity of what would hopefully meet demand, then some sort of relationship like this would be a better choice than putting all the cars in one city or the other, or even 50-50. So let's see if we can figure out where these numbers came from. So here's our difference equations, and we would like to prove that long term we would expect 38 cars in Emporia and 62 in Kansas City. So here's the way of thinking about that, is notice that the limit of the E sub n is going to be some number. So the limit as n goes to infinity of E sub n is, let's call it E. So we're assuming there's some equilibrium. And we will observe that whether I call it E sub n or E sub n plus 1, it's the same thing, E. Because that plus 1 doesn't change the long-term trend. And that would be the same thing for the limit as n goes to infinity of K sub n. We'll call it K. Is going to be equal to the limit as n goes to infinity of K sub n plus 1. So if I take the limit of both these equations as n goes to infinity, all these E's and K's with subscripts are going to be replaced with just E and K, respectively. So we'll take the limit of both sides as n goes to infinity. And so we have E equals 0.75 plus 0.15 and K equals 0.85 plus 0.25 E. Okay, so these equations have become this system of equations. And we also know that the total fleet is 100 cars, so E plus K equals 100. So at first glance, it might look like we have 3 equations but 2 unknowns. But if we simplify these, we'll notice we get the same relationship. If I subtract 0.75 over, I get 0.25e equals 0.15k. And if I subtract this one over, I get 0.15k equals 0.25e. So those are actually the same relationship. And so now I just need to sub one equation in for the other and solve. For example, I could let k equal 100 minus e. So I get, if I combine these two, I get 0.15 times 100 minus e equals 0.25e, or 15 minus 0.15e equals 0.25e, or 15 equals 0.4e. And so if we solve for e, we get 15 divided by 0.4, or which is the same thing as 150 divided by 4, which is the same thing as 75 divided by 2. And now we see the problem is we actually need half a car, but that is roughly 38 cars in Emporia. And then plug that back into our original equation, and that gives us approximately 62 cars in KC. So that's how we can predict the long-term behavior for this system. This is a pretty straightforward system. Our next example, we'll get into a messier situation where we have variable interaction, and we'll do that in the next video. So we'll see you there.